Today we're looking at vector projections. Now, to understand these, if we want to project one vector, let's call it u, and I've got a vector here to show you, onto another vector, let's say vector x, then imagine that u is a wire and the sun is directly overhead or perpendicular to x. So imagine that the sun is shining straight down here. The projection of u onto x is really just looking at the shadow that u is going to cast on x. So if we can imagine that, the sun coming straight down perpendicular to the other vector that we're projecting onto, what we're going to get is a little right angle triangle here, and this vector will be projected down and it will land here. Now, there's a few things we're going to be able to do with this. We're going to be able to make a new vector completely, and we're going to be able to just look at the length of the projection, two different things. We're going to start with looking at the length of the projection because that's slightly easier to work out, and we can use basic trigonometry to do that. And then we'll look at how we can transform the original vector, once it's projected, into a new vector. Now, the notation we want to use looks like this. So if we're projecting vector u onto vector x, then we write the vector x down below. So projecting vectors, what do we do this for? Well, it helps us see how much magnitude and direction one vector has in the direction of another. Now, why would you want to do this? Well, let's imagine that we've got somebody pulling, maybe they're towing a car or something like that, and another person says, hey, I'll attach a tow rope as well and see if I can pull as well. Clearly, if we've got two cars driving in directions like this, pulling on something, then depending on how hard they're pulling, we're not exactly sure, how well we're going to move our object in one direction or another. So looking at how much force can be contributed at different angles on the one angle is really quite helpful in a lot of applications. You might also have situations where, say, you're sailing and you've got the wind going this way, but you're actually wanting your boat to go this way. You want to look at how much force in this direction is actually going to take you in this direction by looking at a projection. Note that if we project u onto x, that's not usually equal to projecting x onto u. So looking at that, if we were projecting x onto u, we'd have to imagine that the sun is shining perpendicular to you. It's coming this way now. And then we're going to have a projection that's going to come down like this and have a right angle triangle this way. So it's not going to be the same thing. Now, what happens if we have our angle being obtuse? So here we had vector x going this way, and we had vector u going this way, and we had theta in here as an acute angle. But if we were to draw that again and make theta obtuse, and our vector is out this way, then our projection of u onto x, if it's going straight down perpendicular to x, is going to land down here like this, isn't it? And we'll get a right angle triangle on this side. Now, if vector x has direction and it's going this way, then what we've actually created is going to be a vector that's coming this direction. So we're going to get a negative vector. But that also makes sense because we're going to be thinking about using the cosine of our angle, and the cosine of theta is negative when theta is obtuse. So we'll see how that works in a moment. So we'll start by finding the length of a projection. Now, we call this the scalar projection because even though it will look like a vector, it won't be a vector with all its direction information there. And that's because we're projecting one vector u onto another x without really having any idea what this vector is, x, and where it sits in space. So we start by using basic trigonometry. We can say that cos of theta is the adjacent side, and I'm calling this the directed interval ON, over the length of the hypotenuse there. So that's the length of vector u. Now, if I want to rearrange this, I can say that the directed interval ON is going to equal the absolute value, or the length of vector u, multiplied by cos theta. That's just basic trig right there. Now, this is going to work even when theta is obtuse, because the cos of an obtuse angle is going to give us a negative answer. This part here will be positive, and so we'll find that ON is negative, and sure enough, it is going in that negative direction there. Now, we've already seen the dot product, and that can help us to tidy up this formula. This one's useful, but we might not know theta. We might know more about the two vectors. Now, we already know that the dot product has a formula like this, which is really similar to the one that we've just generated. So using this formula, which we've already seen in the last exercise, we can say, hold on, how do we make this one look like that? Well, we could divide the left-hand side here by the absolute value of vector x, or in other words, the length of vector x. So we can say that the length of vector u times cos theta is going to be the dot product of u and x over the length of vector x. So now, instead of using this formula that's got cos theta in it, which is a perfectly okay formula, we'll put a box around it to say we've got that if we need it, we can now also say that the directed interval ON can be found with this simple result here. It's the dot product of the two vectors divided by the length of vector x. Now, just as we've already considered that when theta is obtuse, cos theta will be negative, similarly, in that situation, the dot product would be negative. And that's okay, but if we want to find the length of a projection and we want it to work every time, then we could say with this formula, we'd need to take the absolute value of cos theta. So we'd have the length of vector u multiplied by the absolute value of cos theta. And we'd need to take the absolute value of the dot product over the length of vector x. So this formula and this formula will work if theta's acute, and these ones are your backup for in case it's obtuse. But the workaround that you can always use with projections, if you're forgetting these formulas or forgetting how to apply them, you can literally draw both vectors and imagine that sun coming down, hitting the wire, draw your right angle triangle, and you can figure out a lot from that. But this is the formula you want for the length, so let's put a box around that or highlight it, whatever your system is. Now for some examples, we need to find the length of the projection of vector A onto vector B, and we've got a variety of different types of questions here. Now, not a bad idea, especially if you've got different letters than what you're used to and you're just starting out, to put down the two formulas that you might need to use. So for these first three, we need to use the dot product because we don't have any information here about theta. So even though we could find it with a sketch, this is going to be much quicker and easier. And down here we've got theta, so we might need to use that first formula. So the dot product needs to go on the top. So we have the dot product here of A and B, which means we need 3 5s plus one lot of 0. So that gives us 15 on the top. And on the bottom, we want the length of vector B. Now, picture what this looks like. This is a vector that goes along 5 and up, not at all. So if I was to draw it, it's just a line that's 5 long. So that's really straightforward. And here we have an answer of 3. So that means that the length of this projection onto, the length of the projection of this vector onto this one has a length of 3. Now, to check your work, just think about what this means. If I draw this vector, it's going to go along 3 and up 1. So it's a vector that looks like that. That's vector A. Whereas vector B just goes along for 5 units, like that. And so it's sticking out 2 units past. So if the sun shines straight down and projects vector A onto vector B, you can see why it's going to be 3 units long. And a sketch there makes it really reassuring and shows you that you've used the right formula and you're on the right track. And the working is really quite straightforward. So for the next one, we need the dot product of A and B, which would be 5 lots of negative 3. That's minus 15 minus 8 over the length of vector B. Now this one's a little bit trickier. You know the formula for it though. We can either use the square root of negative 3 squared, which is the same as 3 squared, plus negative 4 squared, which is just the same as 4 squared. So I can see here that I'm going to have negative 23 on the top and 5 on the bottom. The other method that we have of finding the length of this vector is to actually just draw it. This vector just goes 3 steps to the left and then 4 steps down. And as soon as you've drawn a right angled triangle that looks like that with 3 and 4, you can see that the other side must be 5. It's a 3, 4, 5 triangle. So that's quite straightforward too. And just thinking about what we've done here and whether it makes sense, we've taken this vector 5, 2, which if I draw it, it's just going 5 units across and 2 units up. That's our vector there, a rough sketch. And we've projected it onto this vector, which goes negative 3, so it goes out there for 3, and then down 4. Now, this is not a very good sketch, and I'm starting to run into my writing, but we've got something that looks like that. So, dropping this onto this, we can see why we've got a negative answer, because the sun is shining down perpendicular to this vector here, vector B, and so we're going to get this vector coming across like this. And what we're saying is that this length from here to here is 23 over 5. What's that? 4 3/5, 4.6. So just looking roughly, I've got 5, I've got 4, 4.6 looks roughly right. And it's in a negative direction because this vector was going downwards this way. So this vector is going in the reverse direction. So a quick sketch sometimes just shows you that what you've done does actually make sense and that you're on the right track. All right, the next one's in component form. So same thing, we need the dot product. So we need 24 plus 7. So we need 31. And on the bottom, we need the square root of 6 squared plus 7 squared. So I've got 31 over, what's that, 36 plus 49, which is 85. So I've got the square root of 85. Bit of an awkward answer, but there it is. Now for this last one, the length of vector A is 6, and A and B lie 60 degrees apart. Now it doesn't hurt to do a sketch here. Let's just sketch it on the side here. We've got 60 degrees, and if we call this vector A and it's 6, then what we're actually wondering is what this length is here. So simple trigonometry will find it. If you've forgotten this version of the formula, it's just rearranged trig from basic year 9. So all we're saying is that we need to do 6 multiplied by the cos of 60. So the cos of 60 is a half. The working is not there because I can't do 6 halves in my head. It's to show the process of how I've done it. And remember, by showing a process, when you're learning, you're reinforcing what that process is.